This
So let us say there
conference
are
will
two
now
classes.
be recorded.
Yes, sir.
Hello.
Yes, sir.
Yeah.
I am receiving.
Generally, sir, put it in a simple way. More or less, many these things are decided empirically depending on the application, sir.
Okay. Okay, sir.
To my knowledge, even the decision trees also, generally we decide, even neural networks also, although some heuristics available, generally mostly the parameters are tuned based on the application and the availability of the data.
Okay. Yes, sir. Thank you very much, sir. Thank you.
Yeah, but there are also some approaches where work for small sample size also. Researchers came out with some techniques where even with a small amount of data also they can they could come out with some classifier.
Sir, can I
Maybe
use yes. Can I use
yes,
small
sir.
number of data for a decision tree? Still, I can get the accuracy, sir. Better accuracy.
Generally, small amount of data training, small amount of data, it may undersample. You may have underfitting. It may happen underfitting, sir.
Okay. Okay. Okay.
Generally,
Sir.
for any classifier, generally it's underfitting happens.
Okay. Okay. Okay, sir. Okay.
Yeah, because it is something like we are training a student with uh, not enough examples, then the students may not grasp the concept. So that is the idea, sir.
Okay. Sir, one more last question, sir.
Yes, sir.
Sir, for ANN, what is the feasible learning rate and momentum I can set approximately? Or should I go trial error method, or I can set some 0.1, 0.2 like that, sir, for learning rate and momentum?
Yeah, again, sir, those are also, maybe you can refer the literature. There are some heuristics in the sense, based on the experience they might have suggested. Yeah, I don't
Okay.
remember those values, sir. So you can, a lot of surveys happen. Maybe you can just refer those, sir, particularly if you want specific values for specific application. But generally, most of the cases, if you are working on specific application, generally we need to decide. The researcher, we need to decide maybe based on some uh, maybe experimental analysis. Right? We don't say trial analysis. Maybe systematically you will increase by step of 0.1 or 0.01.
Okay.
Of
Okay.
course, we
Okay.
also, before
Okay.
that, we also see some general guidelines given by the researchers. Maybe within that limit, again, we need to do some kind of experimental study to decide.
Okay. Okay. Thank you very much, sir.
Yes, sir, yes. Welcome.
Yes, sir. Professor Vijay Kumar, sir.
Yes, sir. Shall we start, sir?
Yeah, you can start your session, sir.
Yes, sir. Okay. Okay. Thank you, sir.
Thank you.
Hello.
Yes, sir.
Sir, can you see my screen, sir?
Yes, sir. Yes, sir.
Will you be able to see entire screen or something is hidden, sir?
Yeah, the screen is visible, sir. No problem.
Complete. Okay. So I'll switch off my video. Maybe. Is it okay?
Yeah, it's fine, sir. You can switch off your video.
No. You want me to switch on my video, or is it off also fine?
Yeah, if it is off also fine, sir.
Yeah, okay. Yes. Dear friends, I could see about 16 participants, right, sir? Yeah, I think that's all, sir. Any more to join?
Probably they may join, sir. Some more will join.
Yeah, what are the total participants, sir? Just for my
So
information.
actually, it is 40, sir. The participants
Okay.
are 40.
Okay. Fine, sir.
Right.
Yes. Yes. Dear friends, good morning to all of you. In fact, it's a very happy to share my knowledge, share my knowledge on the some concepts, advanced concepts related to classification. Yeah, although you may be familiar with some of the concepts I discuss in this session, uh, and probably I welcome any discussion, meaningful discussion on this. Basically, idea behind this advanced concept, choosing the advanced concept in classification in the sense, probably in machine learning, any machine learning workshop, generally the basic course, in the basic course, generally supervised learning and unsupervised learning concepts are covered in general. Just I thought to add some more additional concepts which may be useful to you, and also which may be interesting even to take up further research as well. Of course, I'll not be discussing the algorithms in detail because of the paucity of time. But my objective here is just to give a quick grasp, quick idea of few advanced concepts in classification. And also, meantime, I'll be requesting you to maybe think on some of the uh, cases or examples based on the concept discussed. I request you to participate and give your thoughts. It doesn't. It definitely it is not like an assignment kind of thing. It is some kind of activities which maybe enhance the learning process. So this is how I organized my presentation. Kindly give your presentation. Maybe give your thoughts or ideas in the chat window so that it triggers the meaningful discussion to everyone. Yeah. Thank you so much for the opportunity. Let me take up this. Myself, Vijay Kumar Kadapa, working as Associate Professor and Head of the Department, BMS College of Engineering, Bangalore. In fact, this is just to give a quick profile of the BMS College of Engineering. In fact, it is the first private engineering college in the country. Maybe it's established in 1946, and it has about 13 UG programs, that is very engineering programs, and almost more than 10 PG programs, including MCA and MBA. And it is an autonomous college under Vishweshwar Technological University. And it got all the programs got accredited by National Board of Accreditation. In fact, it is the first college, one of the first colleges selected by the NBA team, under Washington Accord, along with a few NITs. Okay, so and also most of the professors are evaluators for NBA evaluators for various colleges across the country. So with this quick introduction, I would like to go to the next part. Yeah, this is the outline of my presentation. I would like to cover semi-supervised learning, multi-class classification, active learning, transfer learning, and reinforced learning, and artificial neural networks. If time permits, I will take up a few more, maybe association role mining also. I think it's not covered earlier session. If time permits, we'll take that also. Yeah, my effectively my presentation would be about 1.5 hour session, 1.5 hour. Yeah. Let us take up the semi-supervised classification. The semi-supervised classification. Before we take up this topic, I would like to just let us get into this supervised learning. What is supervised learning? Can you, one of you, maybe you can always, when I put some question for discussion, this is only for discussion, not to test your knowledge, definitely not to test anybody's knowledge. yeah, just for generating more and more learning. That's all. So what is supervised learning? And can you give an example of it? You can you can use a chart window for any kind of uh, discussion or interaction. Yes. Hey, can you share your thought? What is supervised learning? And similarly, what is unsupervised learning? Maybe kindly use the chart window. Yeah. So 1 minute. So let me. Yeah, one of you please, or one of you can try to explain, please.
Hello, sir. This is
Yes, ma'am.
Garima Sharma from Graphic Era Deemed to be a University, Dehradun. So,
Yes, ma'am.
sir, the a bit of supervised learning and unsupervised learning I am aware of is like supervised learning has labels and we have predefined classes where we have a data set and we actually try to define our data set on the basis of those labels, or we try to map our data set on the basis of those labels. But in unsupervised learning, we do not have such labels and we try to categorize our unlabeled data in different categories. Where in supervised learning, we have outliers, so it's easy to find out and classify those outliers. Where in unsupervised learning, we actually need to work upon many algorithms to find those outliers. So that is a bit of what I know between the supervised and unsupervised learning.
Yeah, perfectly fine, ma'am. Yeah. Yes. So basically, what is supervised learning? As may I know your name, ma'am? Yeah. As Professor pointed out, supervised learning, put it in a simple way, it makes use of label data. Or let us not get into too many details. Maybe an example could be a decision tree. That is the beauty of the semi-supervised learning. Labeled, and also it makes use of the unlabeled data to build a classifier.
Sir, you are not
Okay.
audible. I'm sorry to interrupt.
Oh, not audible. Okay. Hello. Hello. Can you hear me now?
Yes, sir. Yes, sir. We can
Hello.
hear you.
Okay. Fine.
Yes, sir. We can hear you. Yes, sir. Yep.
Yes, ma'am. Yeah. Yes. So semi-supervised learning basically makes use of both. That is the beauty of semi-supervised learning. It makes use of labeled data as well as unlabeled data to build a classifier, unlike supervised learning and unsupervised learning. So that is a key difference. Uh, and in fact, semi-supervised learning is one of the machine learning techniques which gained importance. It is very gained importance in recent times. And the question could be, I have a question here. Can you, any of you can tell me when this semi-supervised can be appropriate? Because it uses labeled data, unlabeled data also. But you have supervised learning also, unsupervised learning also. You may have the question like, why can't I use supervised learning, or why can't I use unsupervised learning in this context? Why semi-supervised learning is really required? Any guess? Quick guess. Yeah. Okay, fine. Maybe appropriate. Basically, it is when you have few label data. Doesn't even you have enough label data, more label data. Some professor was asking in the beginning. Again, enough. It is very difficult to define. Depends on the context and application also. Yeah, when you have few label data, which is generally if you use supervised learning, maybe it may the model or the classifier is it may not give the appropriate enough accuracy. It is not accurate as well, or we call it as it is underfitted. Underfitting happens. Okay, it is unable to do its task. Put it in a simple way. With a few label data, if you use supervised classifier. And more unlabeled data. That's why when you have few labeled data and you have more unlabeled data, then probably we need to go for semi-supervised learning. Okay, this is the one hint when as to when to use the semi-supervised learning. Let us see few applications where this semi-supervised application is apt. Yeah, generally when you have more unlabeled data and few labeled data, maybe some of the applications could be something like this. You have large unlabeled documents available on the web. Generally, you have a lot of web pages or other articles. If you browse your web, then you will have maybe millions of documents available, right? Those are unlabeled. We don't know which category they belong to. The question is maybe the category in the sense here you would like, again depending on the application, maybe you'd like to classify them into whether it is a scientific literature or business literature. So let us put it in a simple way, whether it's related to business or related to scientific, the science and technology. So likewise, we don't know whether this document belongs to which category. So in that context, maybe we can think of this semi-supervised classification. And similarly, large number of images obtained from surveillance camera. You might have seen maybe in your maybe railway stations or airports or even at bungalows, even house also. Now even the houses or in front of house also we have a lot of surveillance cameras are installed, isn't it? So these cameras, that means we have a lot of feeds in it. Maybe we'll get a lot of videos, or maybe we can get photos and so on. Maybe that's why maybe even if you buy the maybe even gigabytes of memory also, it will run out of memory after 1 or 2 months, isn't it? That's why you have a lot of data available, large number of images and so on available. But how they can be used? But it is unlabeled. Many times it is unlabeled. But from this, we should make out generally the applications could be maybe any suspicious activity is going on, particularly in the surveillance camera. Maybe we would try to find out whether any suspicious activity is happening. Maybe in the railway station, anybody is suspicious. Any person is having suspicious movements, isn't it? Yeah, in those applications we can try to make out. And also speech collected from a radio broadcast. Radio broadcast, let us say you have collected speech, maybe at intervals of every, let us say, a minute or 5 minutes interval. If you take it, then can you annotate the speech, annotation of the speech? It is also generally unlabeled. So that means we don't know what is it all about. Maybe 5-minute speech. Can we describe this 5-minute speech? Can you categorize it? Whether it is related to physics or chemistry or computer science and so on. Some kind of just to give an idea. So these are a lot of speech. Even photos clicked in a rally. Maybe a rally could be in a political rally or any other occasion. You have a lot of photos available which we are not categorized them. Maybe you might have seen in the recent mobile phones, when you click a photo, it automatically categorizes. Nowadays, they are also trying to build some machine learning models into it. You might have noticed it. Maybe if you capture a sunrise, it may click a sunrise, it may categorize it as a sunrise. Similarly, a beautiful maybe a countryside picture, maybe it may say there's a paddy field, right? Paddy field or some other, uh, depending on the scenery you captured, right? So likewise, nowadays even the mobile phone, smartphones also, they have built-in ML models. So now the activity is just, I want you to, I request all of you, please write few more real world scenarios where large amount of unlabeled data is available. So in those contexts, maybe we may likely to use the semi-supervised classification. A few labeled data available and unlabeled data is a huge number. Can you write down, please? Can you write down, and maybe you can discuss? Maybe a few participants maybe try to discuss over phone also. Please take a minute. I request all of you, please take a minute and write down. These are only just to generate discussion. That's all. Otherwise, these are online classes. Unless there is there is no interaction. It's very difficult to engage everyone and learn. Okay? I'll take a minute. I'll read out. Write few more real world scenarios where large amount of unlabeled data is available. I listed few. You can write few more. Yeah, Garima Sharma, like diyas for Deepavali and more colors for Holi. I can just write your comments on the chat window, please. Rainfall happened last year. Yeah, rainfall. So Senthil Kumar sir says rainfall data at various places. Yeah, if it is maybe yes, last couple of years, that's possible. It could be yeah, unlabeled data. Land classification, yeah, very much true. Land classification, yeah, particularly images, satellite images. In the case of land classification, yeah, land generally lands are not categorized as such. A lot of images were taken, satellite pictures, particularly in case of yeah, this particularly ICRISAT will be doing that. Yeah, land classification, irrigation or urban or rural. Yeah, maybe yes, a small label data and maybe a lot of unlabeled data. Yeah, a lot of satellite pictures being taken. Yeah, good. Yeah, there are some. Yeah, maybe any more. Yes, fine. Yeah. Likewise, so the semi-supervised application is. I think now you must have got ideas some when to use semi-supervised classification, right? Yeah. Yes. Now, if you look at this, yeah, if you look at this picture, can you please read out first? Maybe it's the semi-supervised classification. One of the methods. Generally, first step includes it use a few label data and it creates a model like decision tree or any other model. Train the model with label data, available label data. Then you have unlabeled data. Maybe use that unlabeled data. Again, if it is a large, maybe we may not take entire data available. Maybe we can sample it. So then use a train model to predict that labels or class labels for each of these unlabeled data. Okay, that is we call it as actually pseudo that is called as basically pseudo label data. Okay, once you have pseudo label data, once you have the pseudo label data and label data, then now you have more label data. So maybe that more with the more label data, we may construct a better model, better machine learning model. Okay, that means we'll retrain. So using this enhanced added label data, maybe we'll again retrain the model or rebuild the model. That is supposed to give the better classification rate, a better prediction for subsequent tasks. Okay, yeah, this is the whole idea of it. This is called basically self-training. This is basically called as a self-training approach. Okay, build a classifier using label data. Use it to label the unlabeled data, and those with the most confident label prediction are added to the set of labeled data. Okay, yeah, and repeat the process. That means repeat the process means again you'll retrain the model, then take your unlabeled data, classify it, again add that classified data into the label set, again rebuild the model, and so on and so on and so on. At some point of time we can stop this. Okay, then we'll get the better machine learning model using this approach. And other one is you have before we take up the other approach, we'll take this analogy for self-training, particularly to understand semi-supervised classification. In fact, we use in our day-to-day life, we use semi-supervised classification a lot. Let us say in our students, let us take our student example. Student understands the concepts using a few solved problems. That is a machine learning course they would like to learn, but only there is a constructing a model, constructing a decision tree model. Maybe there are only a few solved cases, maybe some data on construction of the decision tree. Maybe likewise, the student understands the concepts using few solved problems. That means it's something like availability of few label data. Next one is based on his learning, maybe he has lot of other problems which are not solved. Okay, that is similar to unsolved case. Unlabeled data. So based on his learning, student solves few more problems for which he doesn't know the answer actually. So those are unlabeled. That means unsolved. So he'll try with the learning what he had with a few solved problems. He'll try to solve, to spend some time, think and do it, and he'll try to solve it. So again, these may be wrong. That's why confident. If he feels that this is the confidently, yes, he did confidently correct, maybe that may be added to the solved problems. Again, he will just go through them, all of them again, once again, try to understand the concept better. Then again, he will take the few more tough problems which are not solved and try to solve them. Then those solutions are added back to the list of solved problems. Then he learns it, and so on. So this is how generally we do it, in fact, because the teacher cannot solve all the problems in the class, right? Only we solve few of them, but students are expected to do expected to solve other problems, isn't it? So this is actually we repeat the process. You will repeat the process, and repeat the process to solve the many more problems. This is one analogy generally the students do in practice. Next one is other approach. If you look at the co-training, other approach under semi-supervised classification is co-training. Use two or more classifiers to each other. This is also, in fact, it is widely used by humans. Co-training. Use two or more classifiers to teach each other. Yeah. Maybe first step is it is something like each learner uses a mutually independent set of features of each tuple to train a good classifier. Tuple in the sense it is some like an object, like a student data. Okay, to train a good classifier, say C1 and C2. Let us say you have two classifiers. You have C1 and C2. Next, and each of these two classifiers make use of different set of features. They will not use for the same tuple. They will use a different set of features, maybe F1, F2, or F3, F4. Feature first two features may be used by C1, other two features may be used by C2. If at all assuming that there are four features. Okay, yeah. Now using these classifiers C1 and C2, try to print that because it's a co-training. We use two classifiers here. These each of them are used to predict the class label of unlabeled data X. Okay, yeah. Next, third step is important, teach each other. The tuple having the most confident prediction from C1 is added to the set of label data for C2 and vice versa. It is how. So let us say classify C1 for a unlabeled data X, it classifies. Okay. Again, it's the most confident prediction in the sense, maybe confident prediction in the sense there may be many class labels, and each class label is given some kind of probability. Okay. Yeah. Then each classifier predicts the unlabeled data X, and that is added to the set of labeled data for C2, and similarly vice versa. It is something like I will classify it and I'll solve the problem, and I will share with this my friend. I'll share with them my friend. I'm teaching my friend. He also solve a problem and he'll share the solution to me, which I'm not aware of. Likewise, it is something like teaching each other. That's why it's called as a co-training method. So in that way also, the semi-supervised learning classification, we can improve the model better. Next one is the co-training example. As already said, if you have considered two classifiers, say C1 and C2, and assume that there are four features, F1 to F4, and maybe features could be like if it is a student-related data, attendance or CGPA, rating in the rating in soft skills like spoken English or rating in written English, and so on for each student. Now each student is a tuple with four features. I have given few features here just for illustration. Assume that there are two classes. Okay, maybe placed or not placed in the campus placement. Label data, if you can take student 1, maybe T11, T12, T13, label is L1. Similarly, assume that there are 9 students are there with the labels. Unlabeled data, assume that there are almost 20 features. Now in this case, if you take the classifiers C1 and C2, C1 is trained on F1 and F3, C2 is trained on F2 and F4 using the label data. Okay, now there are two classifiers. Okay, two classifiers, they teach each other. That's what. So now unlabeled data S10 to S30 is given to C1, and let us say C1 C2 separately, and that classified data, it classifies, each one classifies this, right? So C1, let us say S10 is classified as L1 by C1, then that will be added to the label data of C2. Similarly, C2 also classifies let us say S10, that is added to the label data set of C1. Then these C1 and C2 are retrained, and this process is iterated a couple of times. So this is how co-training happens. Yeah. Now, again there is small activity here. Analogy. Assume that two students are preparing for GATE exam. Explain if co-training can be useful to them in this context. Can you just give your thoughts, just to generate some discussion? Can you give your thoughts whether it is really useful co-training for GATE examination in this context, or it is not useful? Maybe anything is fine. Maybe you can just request your yeah, thoughts on it. Hello. Anyone of you can share your thoughts. Yeah, Vani, ma'am. Yeah, useful. One student preparing for network. Yeah, Professor Vani, say useful. One student preparing for network, other one is DBMS. Later they share. Okay. Yeah. Yes, useful. Rita Koshi, Professor Rita Koshi also said it is useful. Yeah, good. Yeah. Yeah, this is definitely co-training the semi-supervised, because you see, for any course, you need not take two different courses, maybe any course, let us say databases, maybe we have some solved cases, solved examples. We can treat them as, in fact, label data. Unsolved, there are many unsolved examples, right? So each unsolved example can be independently tackled by the two students, and each one of them can share their experiences, right? Share their answers and discuss, right? So in this case, definitely this is where semi-supervised classification is being used, in fact, by humans. That's how even it is propagated to machine learning as well. Okay, yeah. Thank you for your response. Let us continue. Yeah, next, this is a quick idea of the semi-supervised classification. Okay, semi-supervised classification. Now let us take up other. Next one is a multi-class classification. Multi-class classification. So this multi-class classification particularly is very useful when we build binary classifiers. When we have built binary classifiers, in the sense, binary classifiers, let us say SVM, particularly SVM, or and so on. Many, let us say you have some classifiers, but they are binary in nature. Even decision trees, some kind of decision tree is also binary in nature. So in that case, but in real data could be real data may have many classes, actually, not binary, isn't it? But the given classifiers are, they work for only binary classification. That means if you have two class labels. So in that case, how to make use of these binary classifiers for multi-class classification? So that is where this multi-class classification will be useful to us. Okay. So here assumption is you have given with the binary classifiers. Okay, but in real world you have more than two classes, right? You have more than two classes. So how these binary classifiers can be used for that purpose? Now let us get into the details. Yeah, first method, let us see the first method. That is, first method is called one versus all. One versus all method, simple to called as a OVA. That is OVA, one versus all. Then in this case, what happens is we are going to build a classifier. Here we are going to build a classifier one at a time. That means for every class we are going to build one classifier. If there are m classes are there, we are going to have the m classifiers. Okay, so that is the idea behind this. That means given m classes, we are going to build or train m classifiers, one for each class. Okay, yeah. So yes, these m classifiers are binary in nature. Again, think of that. So those are binary classifiers. Next one is, let us say, you may put a question. So you see, binary classifiers means, see, for the given data. So these are the general approach. Okay, already you have built the classifiers. That means you already have the binary classifiers, maybe decision trees or SVM, and label data is available. Okay, but more than two classes available to you. Okay, yeah. Now classifier J. Let us say you have built the classifier J. How to treat? If there are many classes are there, but this classifier is binary, how to build it? So there is you will get a natural question, right? Yeah. So classifier J, let us say you have m classes. Let us say C1, small c1, C1, C2, or theta1, theta2, and theta m. Let us say you are building a classifier J for class theta J. Then the tuples or the data in the class the J, that is theta J, are treated as positive class, and rest of the data belongs to other classes or taken as negative class. So in that way, so now you're distinguished. That means you are separated the given training data, although it is multi-class related. We have relabeled them. In fact, we relabeled them as logically relabeled, not physically. Logically relabeled them as two classes. One is class J. Other that is, one class is class J. The data belongs to actually theta J. Okay, then rest of the data belongs to other classes treated as a negative class. So in that way, you have separated the given given label data into two classes. Then you train this classifier J, because this is a binary classifier. It needs the data, training data with two labels, right? Two class labels. Okay, now this is the approach where you can train any binary classifier. Okay, I think hope you got the point. Yeah, classifier J can treat tuples in class J as positive, and the data or the tuples of other classes are treated as negative class. So positive class and negative class. Now train it, build the classifier. Yes. Now to classify a tuple AX, you want to classify a tuple X, that is a new test data item. The set of classifiers vote as an ensemble A. Now I'll use all these M classifiers, and now you have the X, that is a test data. Okay, test data is given to each of these classifiers, right? M classifiers. Each one of them gives either positive or negative. Each one of them gives either positive or negative. So based on these references, maybe few of them give positive, few of them may give negative. Then find what is the final class label for X. That we need to decide. That we need to decide. How we are going to decide it? Just through, we'll understand it through an example. Let us go to an example. Let us see this example. Yeah, using one versus all, consider 6 binary classifiers related to 6 classes: class 1, class 2, class 3, and so on, class 6. An instance that is a test data instance, P need to be classified now, classified separately using these classifiers, and the decision is obtained as shown in table. You see, now I am giving the data item P to each of the 6 binary classifiers. Okay, and it gives, each classifier assume that it gives some decision, whether it's a positive class or negative class. That decision is shown on the screen here. So there is a binary classifier for binary classifier 1. There is a for class 1, there is positive class it gives. Then classifier 2, it gives negative class. Classifier 3, negative class. 4, positive. Next negative. Next negative. Now what could be the result? What is the final class? 6 classes, 6 classifiers given their decision independently, but what we want is the final one. We need to combine all these decisions. In fact, this is actually an assembly approach. Okay. Yes. Any guess? What could be generally people may take majority here? Is a simple majority voting is enough here? Yeah, okay, maybe let us see the solution. Maybe I'll give the solution, try to think as how it arrived at. Okay. Yeah. Yes, I have given the solution as well. Yes. Yes. You just right hand side table, in fact, it gives a solution to you. Can anybody guess? What could be the solution based on this? Yeah, but what could be the final class label? Each classifier, you see, classifier 1 basically it is for class 1. Classifier 2 it is for class 2, class 3, and so on. Yeah, based on this, can you guess what could be the final answer? I think you might have thought some ideas. Let us see. Let us the first classifier 1 is given a positive class. Then what you should do is, you should for class 1, this is a classifier 1, right? For class 1, you see, this is the first row. If you look at the first row, I have to, if it is a positive class, yes, it will get an vote of 1. Class 1, okay, there's a first column in the right side table, class 1, it basically gets a 1 vote. Rest of them will not get any votes. You just see, rest of them are empty. rest of them are empty here. Okay. Next one, if you took the classifier 2 decision, there is a negative class. If it is a negative class, what happens is, that is class 2 will not get any vote. Other classes will get votes. That is one each. That's what I have written here, 1 1 1 1 1. Okay. Then if you look at the classifier 3, you have negative class. So here also class 3 will not get any vote. In fact, other classes will get vote, and so on. You can do that. Positive class, classifier 4. Look at this is it gets that is class 4 will get one vote. The rest of them will not get any votes. Okay, this how you can repeat. This process is repeated again. Negative score, negative class. So class 5 will not get any vote. Other classes will get vote. That's what here. Yeah, class 5. Yeah, class 5. Yes. Similarly, class 6 will not get any vote. Rest of the class will get it. Likewise, now for each class, you just total it, number of votes. So first class got 5, next 3, 3, 3, 5, 3, and so on. Right? Pick the maximum one, maximum votes. So I think class 1 and class 4 get the maximum votes of 5. Maybe it can be classified either class 1 or class 4. So that is how maybe in the multi-class classification, maybe using 1 versus all, we can classify any tuple P, there is a test data instance, into one of the classes based on binary classification. You have 6 binary classifiers, right? Yeah. Likewise, you can use many binary classifiers to classify a given test instance using ensemble approach. Now let us get into another one. Multi-class classification. Another approach we have is all versus all. Look at the second one. This is all versus all. Yeah, all versus all. Here you learn a classifier for each pair of classes. Earlier what we did, a particular classifier maybe for that class and rest of the classes. That's how we have trained it. Okay, here for every pair of classes, there is a class 1, class 2, you will build one classifier. Class 1, class 2, another classifier. Class 1, class 3, another classifier. Likewise, choose all the combinations of a pair of classes. For each of this pair, you need to build a classifier. Then this classifier is trained using the tuples of those 2 classes only. Okay, a classifier is trained using the tuples of those 2 classes, because this is a binary classifier. It needs only 2 class the label data for 2 classes. Okay, yeah. So this is very simple one, but you need to have here many classifiers. So in the previous case, if there are 6 classifiers are there, you will 6 classes are there, you need to have 6 classifiers. Whereas in this case, 6C2, that means 6 into 5 by 2, that is almost 15 classifiers are required in this all versus all approach. Here more classifiers are required. So then in this case, to classify a tuple X, each classifier votes. X is assigned to the class with the maximum vote. So here majority voting is used. Okay, majority voting is taken into consideration to combine the decision from each of these m into m-1 by 2 binary classifiers. Let us see an example. Yes. See, let us take the case of 4 classes. An instance P is classified using these classifiers to distinguish a pair of classes as shown below. That means I have given an instance test data instance P to each of these. There is 6 classifiers. That is 4 into m into m-1 by 2, right? 4 into 3 by 2. That is, you will get 6 classifiers for every pair. Okay, for every pair of classes. Now there are 4 classes. I'll label them as, let us assume that those classes are CL1, CL2, CL3, and CL4. Now I'll have a classifier in the table. If you look at it, first row, classifier 1 for classes CL1 and CL2. Similarly, CL1, CL3, CL1, CL4, CL2, CL3, CL2, CL4, and CL3, CL4. Likewise, every pair of classes, I have taken one classifier. Now that is built. Okay, that already trained. We assume that those have been already trained. Maybe it could be a decision tree or SVM, maybe any binary classifier for that matter. So now P is given to each of these classifiers, and it gives a decision. The second column gives a decision by the corresponding classifier. Okay, Yeah, in the first case it is given as Cl1, second case Cl3, and so on. The last case it is given as Cl4. Now, can you tell me the third step? What could be the decision as a final decision by these ensemble of classifiers? That means P belongs to which class? Anybody? Can you please write your answer in the chat window, please? It's pretty straightforward. Professor Vani says it is Cl4. Yeah. Let us see any other responses. I took no other responses. Okay, one may miss. Cl4 is perfectly fine because we'll poll the votes for each class. That is Cl1 1 vote, Cl2 1 vote, Cl3 1 vote, Cl4 3 votes. You can just count the votes for each of them. Cl1 is repeated only once, right? Cl2 only once, Cl3 once, Cl4 thrice. So Cl3 got 3 votes. So can you please once again explain? Okay. Yeah, just see in this classifier, see here in this multi-class classification using all versus all versus all, let us say if you have 4 classes, we are going to build a binary classifier for every pair of classes. Okay, in this case every pair in the sense it is something like 4C2 you will get 4 into 3 by 2, that is 6 classifiers you will get in this case. But in general you have m into m minus 1 by 2 if there are m classes. So now if you look at the first row, it is a classifier, binary classifier for classes CL1 and CL2. Next, another classifier for CL1 and CL3. I am taking just pair of classes. For each of them I am building a classifier. So in this case it is 6. I think that is clear. So then build those classifiers because you have only 2 classes. There is a pair of classes. Those label data is available to you. You build the binary classifier. Next one is, yes, once you have all the 6 classifiers ready, then you want to predict the class label of a test instance. Call it as P, isn't it? Now this P is given to each of these 6 classifiers, and that each classifier will give a decision. Okay, that decision is shown in the table as a second column, right? Yeah. So I think that point is clear. Now take the majority, take the count for each of the classes. That is a CL1. There are 4 classes for CL1. So you just see CL1 is predicted by any classifier. How many times it is predicted? Only once, right? First classifier predicted the decision as CL1. So one. That's all counted. CL2 only 4th classifier did it. So 1. CL3 1. CL4 that output is given by 3 classifiers. So 3. So which one got the maximum vote? Which class got the maximum vote? That is CL4. I think hope it's clear. Garima ma'am, it's clear? Yeah. Okay. Thank you. Yes. So that is how we want to make it. Let us say if I change the decision. Let us say can you? I'll just change the decision as, let us say, in the place of last CL4 and CL4 last 2 decisions, if I change it to, let us say, CL2 and CL3, what could be the answer? If I change last 2 decisions as CL2 and CL3, what could be the decision? Just I give another case where if I change last 2 rows, last 2 decisions as CL2 and CL3, what could be the final decision in that case? Just poll it. That's all. You just count the vote for each of the cases. Yeah, correct. Yes. I think Garima. Because Garima says it is equal to correct. CL2 or yes, correct. It is equal to 2 and 3, so it could be either CL2 or CL3. Yes, that is the majority voting. Maybe anyone can be picked up. That's all. Yeah, that's absolutely correct. Yeah. Now let us continue. The other one is, you see, under multi-class classification, one more approach is that is also a very pretty straightforward approach. Error correcting codes. I mean, that is not random actually. It may be picked up anyone ideally manually, but generally, when you code it, it depends on the coding. Whether it picks up first one, second one, depending on the coding, it will be taken. Or if you pick randomly, also depends on the coding. That's all. Anyone is fine. Yes. So now let us take the error correcting codes. Third approach is error correcting codes for multi-class classification. And if you look at here, yeah, this example is just there are 4 classes is taken, and error correcting code word is given for each class. Okay, this how first column indicates class label. There's 4 classes, and rest of the columns put together we call it as a code words. That means each row indicates a code word for that particular class, right? And each column, in fact, each column, there are 7 bits are there in each code word. If you look at here, there are 7 bits are there. Okay, each bit, there are 7 bits are there. We need 7 classifiers. Actually, we need to have 7 classifiers for each bit in this approach. For each bit of the code word, we need to have a classifier. So in that case, 7 classifiers are required. Yeah. So you might have heard about error correcting code, maybe in the communication, particularly in the communication, maybe originally designed to correct errors during the data transmission for communication tasks. Of course, by exploring the data redundancy. Yeah, this version for each class, a code word is associated. That's what I explained just now. For each bit, there is a binary classifier. For each bit, we need to train a binary classifier. In this case, there are 7 classifiers because there are 7 code word. If you right hand side, if you look at here, error correcting code word, right? There are 7 bits, so you need to have 7 classifiers. Next, you might have heard about Hamming distance. So we are going to use a Hamming distance approach here to find out the final classification, right? So Hamming distance, already most of you is very clear to you. This is a number of different bits between 2 code words. That is called as a Hamming distance. If you, let us say, C1 and C2 related to that, if you take the C1 first 2 rows in this example, yeah, what could be the Hamming distance? Number of different bits between 2 code words. You should take only corresponding bits. If they are same, you should not consider. Last 3 bits are same. I think first 4 are different, right? If you take the first 2 code words, then in that case, what could be the Hamming distance? It is 4, right? It is 4. Similarly, if you take the C1 and C3, that is the first and third code word, what is the Hamming distance? I think first one is different. If you take the first 1 0 1 0, so 1 1 no same, 1 1 so 1 0 1 0. In this case also 4. Okay. So likewise, even first and third also Hamming distance is 4. So that's how these are some of the basic concepts. Let us take the same example for prediction. Yes. If you look at here, a 7-bit code word is associated with 2 classes. Each class, you may put a question how the code word is decided for each class. Maybe here we are assumed that is again a designer of these code words. Maybe there is again a specific way of doing it. Okay, there is not. I'll not get into those details. Okay, just I want you to give an idea about how classification works, right? Yeah, let us not get into the design part of code words and so on. That leads to a lot of communication theory and so on. Let us not get into that. Yeah, so assume that code words are already decided for each of the classes. So now I would like to predict. So for a given tuple X, there is a test data instance. I want to predict the class label of X. Okay, I want to predict the class label of X. Then this X is given to each of these 7 classifiers. Each of these classifiers is given. Then output. Assume that the output is given as 0001010 by these 7 trained classifiers. First bit is given by first classifier, second bit second classifier, third bit is in the output. Third bit is given by third classifier, and so on. Okay, so this is how this output is given. So now you have again this is the output code word for the test data instance. Now what is the class label for this output code word? This output code word is related to X, that is a test data instance. Now what you need to do is, the procedure is, we just find out the Hamming distance between this output code word related to test data instance to each of the code words, each of the code words related to the classes, given classes. Let us say C1. So Hamming distance between the code word of C1 and the X. Similarly, Hamming distance of there is code word of C2 and X. Similarly for C3 and C4. Just can you find out the Hamming distance? Please take a minute or so. Please can you find out the Hamming distance between 00, that is 0001010 and each of these 4 classes? Five. Divakar's sorry. Hamming distance is 4. Divakar says it is 4. Correct. Earlier one probably. It's for addition. Okay. Divakar says, Professor Divakar says every 5 tree. I want to find out. I want you to find out for each of these 4 classes. So you will get 4. Yeah, correct. Now, Vani madam says, yeah, Divakar sir said 5 3. Only for maybe first 2 classes he might have told. Vani madam says 5 3 3 1. 5 3 3 1. Yeah, again, Divakar says for third class probably it is 3. Yes, correct. Yeah, yes. So yeah, if it is 5 3 3 1, yes, let us. Yes, first one you see all are ones, so here you will get 5. Correct. There are, because between the first class 1 code word and this output code word, there are 5. That means 5 different words, different bits, right? Corresponding bits. That is 5. Perfectly fine. Similarly, second and the output code word, this is 3. The first 3 are common. Fourth one is different, 0 and 1. So there is 1 difference. Next one, fifth one is also different. Yeah, sixth one is same. Seventh one is different. So 3. Likewise, 5 3 3 1. If 5 3, maybe others also 3 1 might have. Last one, let us check. 0 1 0. Second one is different. Third one is same. Fourth one is same. Sixth one, yeah, 0 0 1 0 same. Yeah, correct. There is only one bit is different. That is the second one. Rest all same. So 1. Yes. Now pick the. Now what could be the class label now? Yeah, this is a Hamming distance. Yeah, Hamming distance. Yeah, 5 3 3 1. Perfectly fine. Yeah. Now you pick the one with the least Hamming distance. That's all. Pick the one with the least Hamming distance. Now in this case, Hamming distance of X comma of C4 is equal to 1. That is a class 4. So the given test data double X belongs to class 4. That is the final answer. It belongs to class 4. Yeah, let us move on. Yes, Garima also says 5331. That's perfectly fine. Yeah, good. And now let us get into this now activity. Yeah, or maybe if you have a little more patience, maybe you can just take yeah, maybe at least one. I have given classify the following outputs given by 7 classifiers. Maybe at least you can take for the first one, at least one you can do it. 0010101 or any one you can take it and give. Yes, just for practice. Sir, minimum weight of code is can you try the first one? Yeah, the first or second one. If you can try all three, that's good. I'll take another minute and then we'll go to next one. I request all others also please try out, because I could see only 3 or 4 participants responding. I request all others also please try out so that we can understand the concepts better. Divakar sir has given something. Sir, minimum weight of code is equal to Hamming weight, sir. Sir, here, see, for each class and the given output code word, we'll find out the Hamming distance. Pick the minimum one. In this case, 1 is the minimum Hamming distance, right, among all the classes. So take the corresponding class. That is C4. That's all. That is how we need to take a final decision. Okay, I think you must have worked out. Let us move on. I didn't see anybody responded. Okay, fine. Maybe you can take it as maybe later, right? Okay, let us move to the next part. Active learning. Divakar sir responded 5421. Yeah, maybe. Yeah, but I didn't calculate. Maybe you can calculate. Then in that case, yeah, sir is asking, is it correct for first one? But so similarly, you can try out, sir. Maybe it must be correct. 5421. Yeah, sir. First one not 5. Actually, if you take the first code word, it is 4. Because only four different words or 4 different bits are available between C1 and first one. That you can just cross check, sir. I think first one is not 5, it is 4. Yeah. Now let us move on to the active learning. This active learning, in fact, if you look at here, this is quite often. In fact, many of these methods, what we are discussing, is used by humans. Right? Yeah. In this case, let us look at, just have a quick glimpse of this picture. Yeah, here also you have, if you look at here, L, there is a label training set, and you also have unlabeled pool of data set, that is called U. So in the label training set, using label training set, we'll build a machine learning model. Okay. Next, this machine learning model, yeah, for this machine learning model is built, fine. Then you have, next step is you have unlabeled pool of data. That means you have a lot of unlabeled data. In this case, yeah, maybe the label training data is not enough to build a given machine learning model. Okay, then we need to use the unlabeled data also. Okay, but we don't know the labels. Then what to do? What to do? The question is next, and what to do in the sense we'll seek opinion of some expert in the field. Okay, let us say if you take the medical field, there is a healthcare, particularly tumors, tumors or particular type of cancer or any disease, rare disease. Generally, what we do, we hardly have, in fact, generally label data. So that is called, in fact, a class imbalance data. In case one class have more data items, another class have very few data items. Okay, yeah. So one of the examples is a fraud detection, or maybe tumors, brain tumor, or maybe any rare disease data is generally known to be imbalanced data. That means less labeled data is available. So in that case, more unlabeled data. Then what we do is we will select, let us say, one instance of unlabeled data and given to the expert. That's called oracle actually. Or expert. We'll ask him or her, what could be the label for this? Which this particular, let us say, image of a tumor, let us say MRI scan of that image is given. Then that doctor says, expert doctor says, oh, this is a tumor is present. So then it is labeled. Now that image is, that data item is given, that is put back to the label training set. In that way, we'll improve the label training set. Improve in the sense, increase the number of label training set items. Then you'll build the machine learning model. If it is yes, if it is yes, giving enough accuracy, that's fine. Otherwise, again, take few more, few more unlabeled data items. Then give it to the experts. They will label it. Then add this label data to the existing label data L. Then train the model. Okay. Yes, if it is enough, yes, that training model is accurate enough, then stop. Otherwise, again, take few more unlabeled data and so on to it. But generally, what happens is here, the serious limitation is selecting the which unlabeled data, because we cannot take entire unlabeled data on and seek the opinion of the experts, because they may not have time to do that. That's why we need to take only few unlabeled data. We need to take only few unlabeled data for this. So which unlabeled data is to be taken? That is one, in fact, one of the research challenge in this active learning. Okay, yeah. So this is basically idea behind the machine learning model. Yeah, that's what. Yeah, that's what I said. Class labels are expensive to obtain. Active learner, human, or generally query human for labels. Pool-based approach like use pool update. That's the same thing I explained here. Okay. Yeah, generally what happens is, if you have more data, generally you will get the better model. So more the data, generally you will get the better this thing. But we cannot ask the expert, we cannot give the more unlabeled data for expert to annotate or maybe label it. So it is also expensive. They may not have time. That's why one of the research challenges is how to choose the data tables to be queried for queried to the human. Okay, one thing is uncertainty sampling. One of the things is uncertainty sampling can be used. Choose the data, unlabeled data, which are least certain ones. Okay, we least certain ones. That means they're not clear. See, if you can easily guess the label data, also you have the least certain ones. That means uncertain ones. So again, choosing the uncertain is also not very easy task. Okay. So this is one of the research challenges in active learning. Now the activity for you, yeah, simple activity. So what is the difference between semi-supervised and active learning? Anything common between? Anything common between them? Think for a while. Unlabeled data set. Professor Garima says unlabeled data set. Yeah, unlabeled data set is, yeah, you have common labeled data set also available in semi-supervised. Here also you have label, not on label also there. Yeah, Anything is common. Just can you quickly find out what could be the difference? See, in this case, yeah, I think yes. Okay, let us move on. Yeah, in this case, difference between semi-supervised and active learning here is, if you look at here we are going to use the human annotator. See, for labeling is done here. In the semi-supervised case, will not involve any human expert or maybe another expert to give the labels for unlabeled data. Of course, entire unlabeled data, we may not use it. Only very few unlabeled data required for machine learning building accurate model is taken. That means we will try to use as less, that means as much as less as possible unlabeled data in this case, because human is going to give the labels for them. So the time is, because of the paucity of time, he may not be able to annotate or give label to all the unlabeled data. Okay, so here human expertise is used, but in the semi-supervised case, we are not use it. But in fact, you can treat it as active learning is also a case of semi-supervised, because here also use both labeled and unlabeled data, isn't it? We'll use both. So semi-supervised also use both the cases. That's why the name semi-supervised. So it is a special case of semi-supervised learning. We can treat as such. Okay. Next one. Let us. That's about a quick idea about the active learning. Now let us get into transfer learning conceptual framework. Yeah. If you look at traditional learning framework, I'll just. Yes, this is a traditional learning framework. Generally, this is how we do it. For each task, you have a learning system. Maybe each task, in the sense, you have a data. Let us say
Hello, sir.
character recognition. Hello.
Is active learning same as reinforcement learning?
Sorry, ma'am. Can you repeat?
Is active learning same as reinforcement learning, or is it different?
Yeah, no, ma'am. You see, reinforced learning, I will come to it later, ma'am. Maybe last part of it will do that. No, it is different. It is a special case of, we can take it as it is a special case of semi-supervised learning.
Okay.
Okay. Reinforcement learning generally we may not be using any label data as such. It's more of trial and error kind of thing. In the reinforced learning, then the reinforcement learning is more of bringing out the creativity of the classifier. That's what they say. Okay, that's just to give a quick idea about reinforced learning. I will discuss, ma'am, maybe after 10 minutes or so. We'll be discussing reinforced learning as well. But you can treat active learning as a special case of semi-supervised learning. Yeah. So now in this case, transfer learning, in the traditional learning framework, what we have is, for every task you have a machine learning. Maybe it is a task in the sense, let us say you want to recognize Telugu characters, you will build a machine learning model for it, a separate OCR or machine learning model. Similarly, for let us say for building OCR for, let us say, Kannada, or character recognition system for Kannada, there is a task you would like to build a model for that Kannada. Then you will build a separate machine learning model for Kannada script, and so on. So likewise, for each task, ideally we are going to build a separate machine learning model from the scratch in the traditional learning framework. But if you look at the transfer learning framework, just look at this picture, and can you make out what could be the difference now? Can you think of it? The target task here is, I would like to finally design a classifier for this target task. And source task, in the sense, you already have classifiers for source task. assume that you already have source classifiers are the machine learning models for source task. I think hope you must have got. Yeah, if you have any thoughts, you can put it on the window. Yeah. Okay, let us continue. Yes. Now, if you look at here in this transfer learning framework, some of the tasks you see, let us say I have given an example. You assume that for you have a character recognition model. You build already a character. Let us say for Kannada, you already have a classifier as a OCR. Optical character recognition system is available for Kannada. Yes. Now I would like to. My target task is I need to build a machine learning model for Telugu. Okay, Telugu. Now, can I use, idea here is, can I use the knowledge or the learning happened for the Kannada task, the Kannada recognition system. So Kannada recognition system already in place. It is a machine learning model for Kannada recognition is already in place. Can I use that knowledge for building a classifier for recognizing Telugu characters? If it is yes, then that is actually basically called as transfer learning framework. That is called as a transfer learning framework. I think you must have got the idea about the traditional one. And in the traditional one, you will have separate learning model for Kannada, one separate learning model for Telugu. But you will not be using the knowledge gained from Kannada classifier to learn Telugu classifier. Okay, as a to build Telugu classifier. That's how it goes. So this is the same thing I have illustrated here. Okay, yeah. Extract knowledge from one or more source tasks and apply knowledge to target tasks. That's all. Traditional learning, build a new classifier for each new task. Transfer learning, build new classifier by applying existing knowledge learned from the source task. So these are very, you have very good amount of applications where this is very useful, particularly when the data is outdated. Let's say you have built the data earlier. So but you have added some data. You want to, in the traditional framework, you have to start from the scratch again. You will not use the knowledge gained for the earlier data. Okay, so that is in fact pretty difficult or pretty unwise, right? It is unwise because you are completely discarding the previous model. So when the data is updated, maybe use the knowledge gained in the previous version and try to train the model and use that and train the given classifier only for this new data updated, isn't it? New data updated. You don't again just retrain from the scratch. So even the distribution changes, the distribution of the data changes. Okay, that means more or less for every class. For a particular class, earlier it was 1,000 examples were there. Now few more are added. Okay, likewise the distribution also may change over a period of time. Okay, because of additional data availability. Okay, additional data is available. In this case, web document classification, you have a lot of documents are added to the web, right? Online documents related to, you maybe take it, you may be creating some documents to your students on, let us say, machine learning. Today you will create some document, tomorrow you are going to add few more and so on. Okay, so likewise when the data keep on updating, you need not build the machine learning models from the scratch, but you can use the knowledge obtained from the previous models. Okay, similarly email spam filtering, because emails are keep getting updated, only just take the emails, the new emails, and train the model for these new emails. Okay, so that is the idea. So let us take and you might have wondering, this transfer learning is become very popular in recent times, particularly in deep learning context. You might have heard about pre-trained models in deep learning, particularly in CNN, convolutional neural networks. particularly what happens is you have multiple layers in the deep. Generally, deep neural networks mean to say you have many layers deep. That is, that network is deep. Generally, if it is more than 3 or 4 hidden layers, generally we call it as deep. Of course, deep again, how deep it is again depends on context. Generally, more than 3 or 4 hidden layers, it is known to be deep neural network. So you have many neural networks. In this case, you see, you have a deep neural network. You are trained for, let us say, Kannada script, and can use it the same or maybe the pre-trained model. This is pre-trained model for Telugu task. In this case, what you need to do is first few layers, particularly except the last layer. That is, last layer is known to be fully connected layer. Except that fully connected layer, rest of them probably you can use as it is. That knowledge, those layers or those weights can be used as it is. That is trained for Kannada character recognition, and retain them first few layers, and only train the last layer, fully connected layer, for recognizing the Telugu characters. So in that way, you will be saving lot of time also. Lot of time can be saved. Of course, accuracy, you may not find a big difference in terms of even accuracy as well. Okay, that is how the pre-trained models are very popular nowadays. Even for computer vision tasks, for image recognition tasks, lot of available. Maybe you can, even you can search over the Google, you will find lot of examples on it. Okay, particularly in the driverless cars, road sign recognition and so on. These pre-trained models, or this transfer learning, is very predominant, and it's quite useful. It's one of the active research areas also. Yeah. Now look at this. Some of the example: classification of TV reviews data by using camera reviews data model. See, I have camera reviews data available. Camera reviews in the sense, maybe in the Amazon or maybe Flipkart or any other e-commerce site, you have reviews, right? The customers give the reviews for the items purchased. Let us take the cameras. They give the reviews, and these reviews categories. I built a model for it, a machine learning model, to categorize whether it is maybe poor, good, bad, excellent, outstanding, and so on. So that data is available. Can I use this trained model for camera reviews? Can I use that model knowledge for building TV reviews data? TV reviews data model. Can I use it? Yes. If you can use it, then it is called transfer learning basically. Okay, it is a transfer learning. Generally, classification of Telugu characters by using Kannada ML model. That's how we have been discussing. Okay. Similarly, now activity. Can you come out with an analogy or scenario where humans use transfer learning? Can you think of it? We are using, in fact, we are very expert in this area, transfer learning. Can you come out with few examples or maybe cases? Please think for a while, because this is very interesting. This is how we can learn. Yeah. Take a minute or so. Please take a minute. Just take a minute and please put your thoughts on chat window.
Hello. Hello, Professor Vijay Kumar. Hello. Hello, Professor Vijay Kumar. Sir, are you there?
Yeah. Okay. Yeah. I got 3 responses from Professor Wani. Preparing recipes using transfer learning. Yeah, recipes. Yes. That means one recipe, knowledge gained using one recipe can be used for other recipe. That's maybe the idea. Let us say if I know how to prepare, as a tomato dal, I can use also for to prepare other type of dal. Okay, yeah, tamarind dal or maybe other vegetable you can put it, right? So yeah, good. That can be used. Games. Yeah, one game, learning gained from one, knowledge gained from after playing one game can be used for other games. Yeah, maybe, yeah, maybe all the may not be the games, maybe related games we can take into consideration. Related games, right? The board game, one board game can be maybe that knowledge gained while playing one game can be used for playing other games. Yeah, problem solving. Yeah, definitely problem solving is also one area where if you have set the problems, more problems you solve, maybe you will also get more knowledge to solve other problems as well. Okay, good. Yeah, we use a lot, in fact, and so learnings were very much relevant. What 3 professors commented on it. Yes, really good to see your response. Yes. So this is basically transfer learning, but in the pre-trained models, particularly in the context of deep learning, in fact, it is very much predominantly used in the industry. Pre-trained models. You can Google it. Pre-trained models. Maybe you'll get a lot of cases. Even for Python code also available for it. Maybe if you want to do some hands-on also, want to try out some hands-on also, you can definitely do that. Next, let us move on to, yes, yeah, I have few things like use of mobile phones. I thought of some use of mobile phones. If you know how to use one type of smartphone, the next other smartphone also can be used. Although some small changes are there, but still you will be able to do it, right? Same teaching courses. If you teach one course, there's one programming language. Maybe teaching other programming language may be quite easy, isn't it? Yeah, likewise, teaching courses also we can use it. Understanding languages. Let us say a particular related language, like if you know maybe Tamil, maybe it's easy for you to learn maybe Malayalam. Similarly, if you know Telugu, maybe it is easy for you to learn Kannada and so on. That's how maybe you can think of. Likewise, many cases we can do that. I think one more response we got from Professor Divakar, monthly analysis. Spend analysis, is it, do you mean, I am not sure what is monthly analysis, maybe monthly spend analysis probably. Yeah, yeah, that can be, that could be, yeah. On riding bicycle, you see, if you ride the bicycle, if you know how to ride a bicycle, yes, definitely it will be easy for you to ride two-wheeler. If you know riding two-wheeler, it will be easy for you to drive four-wheeler, right? Straight away learning four-wheeler may be a bit difficult without knowing two-wheelers, because at least you know gear patterns, gear, what is gear, how to apply, and all will be clear to you if you know two-wheelers before learning four-wheeler. So in fact, humans are very yeah, predominantly we are using, yes, in fact humans are very good at transfer learning. Yes, I think this is about the quick idea about the transfer learning. Yeah, let us get into other topic, the last topic probably, or this is reinforcement learning. There's a reinforcement learning. Yeah, if you look at, yes, reinforced learning, just can you see this image and take a look at it, this image for a while. Yeah, just see the components of the diagram and also the arrows. Arrows, you just see, can you, if anybody has some idea, if you can make out some sense out of this, can you please, would you please make out? Yeah, okay, fine. Now let us move on. Yeah, reinforced learning, basically the idea is, in the reinforced learning, there are basically we have learning agent. Yeah, learning agent means it's maybe a computer or maybe a AI, artificial intelligent program. That's what we call as agent, or it could be a robo also as well. Okay, yeah, you can think it is a robo or AI agent. Okay, yeah, this agent basically would like to learn, Okay, that is through reinforcement method. Okay, so in this method, what happens is the rest of the things, the environment in which they learn, basically called pod based environment. Maybe if you take the analogy of riding a bicycle or riding a vehicle, so riding bicycle, if you take it, riding a bicycle, maybe the person here is nothing but an agent, the person who is would like to learn riding a bicycle, and the environment could be maybe the other parts, maybe the roads or the pedestrians and so on. Okay, obstacles, whatever, this all makes a part of the environment. Okay, in this case here, what happens is the maybe the person may have basic idea about as to how to ride a bicycle, but he never drove it, right, never rode it. So they started learning, oh, they'll pedal, they know how put a pedal, legs on, pedal it and try to press, so all those things. Then they try to pedal it. Then initially what happens, they fall down, they may fall down. Yeah, they may fall down. Then once they fall down, they'll get a reward or punishment, right? Once for every action, the action is nothing but they try to ride it, that is action here. So they'll get a reward or punishment. Maybe when they fall down, they may get a punishment. Yeah, that's true. Models to make a sequence of decisions. So perfectly fine. That's what. So then once that is done, what happens is they'll get a punishment. Is maybe they'll get some small injuries, or maybe the father is maybe standing side by observing you. Then they may shout, oh, no, that is not the way. They may give the feedback, right? That is basically a punishment or reward. Then, oh, they think that the agent learns from that. Oh, this is not the way to learn. Okay, because punishment received means this is not the way to learn. They may try to correct. And maybe they pedal it again. This is not the way to pedal it. they'll think for a while, and maybe the person will try to peddle it again. Maybe slightly they may move a little ahead and they may fall it. Or they think that, oh, it's slightly, the father says, oh, here the interpreter, the father is nothing but an interpreter. So they'll say, no, 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 okay, it's okay, but still you need to do this way, that way. They'll give some kind of suggestion, so they may give it, or there's no suggestion, but they give the feedback, interpretation. Okay, that is basically state. Okay, so that what is the appreciation is nothing but a reward here, or maybe they blame or they shouting, or they scold you. Maybe the father may scold you, that may be a punishment, or if you fall down, the injury may be a punishment, or if you move ahead a little bit, that kind of a joy you will get could be a reward. So likewise, you see, for every action you do, you will get a reward or punishment in this approach. That feedback will help us to learn. Okay, help us to learn by trial and more of it is like a trial and error fashion, isn't it? So in this way, the agent, try to learn even in the machine learning also. Okay, here we need not have any label data as such. Label data is not required. As somebody said already, it is a sequence of decisions, the actions, action, this action, next, and that means you will drive the vehicle. Next step, you will try to pedal it with corrected action, and so on and so on and so on. The sequence of actions, particularly it is modeled using HMM, that is hidden Markov models. Okay, so this is basically one thing, and this is a source from Wikipedia. There's an area of ML concerned with how software agents ought to take actions in environment to maximize the notion of cumulative reward. Finally, the person who is riding the bicycle to get maximum appreciation, or they should get maximum joy. That is the objective. When they get maximum joy, when they ride a bicycle maybe over a kilometer without falling down, right? So that's how that is the objective. The agent learns to achieve a goal in an uncertain, potentially complex environment. Okay, it is in the complex environment. Maybe riding a bicycle also not very easy on the road, right? There many people are coming in, vehicles are coming in, the roads is not good, it is not smooth, or maybe up and downs are there. Likewise, it is generally a complex environment. A game-like situation, even playing a game also not very easy. Okay, playing a game also comes under reinforced learning, game-like situation. We don't know what step need to be taken. It is not prefixed many a times. It is not known in advance, right? Employs a trial and error method to come up with a solution to the problem. Gets either rewards or penalties for actions it performs. So that's how it goes. Okay, this is a quick idea about the reinforced learning. Yeah, some applications maybe we can understand better by through some applications of reinforced learning. Yeah, let us just see applications in self-driving cars. It is very similar to riding a bicycle, right? Your self-driving car, there is no driver here. Okay, the roads need to be maybe the roads you have the environment includes maybe pedestrians or road signs, maybe road boundaries, customers moving around, maybe the other vehicles may be coming in front or sideways and so on. They all constitute it. So this is also an example of reinforced learning, particularly self-driving cars, even deep learning also very prominent in this area. Road sign recognition, one of the things, boundary recognition, and so on. For all this purpose, we can use the reinforced learning. Next, industry automation. In the industry automation also, AI agents that is, we can create an AI agent by there is a deep mind to pull. Then the Google data centers use deep mind, an AI agent. Okay, by through reinforced learning approach. This led to a 40% reduction in energy spending. The centers are now fully controlled with the AI system without human intervention. So likewise, industry automation also, particularly robots, other AI agents, we can use it for various purposes in the manufacturing and so on through reinforcement learning. Many times what happens is they learn by itself, okay, through trial and error fashion also. Healthcare, if you look at the healthcare, maybe patients can receive treatment from the policies learned from reinforcement learning systems. Okay, maybe maybe it is something like a special case of expert system where patients generally based on the patient's information received, maybe a lot of diagnostics based on that. Maybe they may get the treatment, intended treatment from the oral system. Gaming, AlphaGo Zero. In fact, AlphaGo Zero is a model which is able to learn the game of Go from the scratch. It is a board game. Go is some kind of board game, and in fact, it is defeated. This agent, there is a program, maybe software agent, defeated world number 1 Kijio. In fact, there is in the gaming also a lot of reinforcement learning. You might have also heard about Deep Blue, IBM Deep Blue. Maybe there's a chess. There's a computer. The computer defeated the world champions in chess as well, Gary Kasparov and so on. So maybe there also reinforced learning is very much apt, where there is no way. See, given the situation, various moves of the pawns, maybe now the program need to take the decision, right? Sequence of decisions. So it is not. It need not be fixed. It may not be fixed, like based on the particular context, but that particular situation, it need to take. It need to take the decision to move the pawn. Okay. Likewise, reinforce. There are many applications of reinforced learning. In fact, humans, we do a lot reinforcement learning. News recommendation to users. You see, each person, each user, reader, each reader is different, right? I want political news or maybe sport news. Somebody knows both. Somebody knows just to have a quick glance of everything and so on. So based on the users' habits or their choices, the system need to recommend the news. Yeah. Now maybe if you can write few, maybe another a minute, write some application. You can think of, maybe due to paucity of time, I'll leave it to you. You can think of some of the applications of reinforced learning. Okay, and maybe if time permits, maybe you can also think of just implementing some of the RL system in Python. I think it's now. I'll take another 5 minutes to close. Yeah, this is an additional topic. Yeah, I think the topics planned, the outline is closed. Now, just I'll give a quick glimpse of this classification by artificial neural networks, because this will be a basic concept required for deep learning. Yeah, backpropagation, particularly backpropagation neural network. It's a neural network learning algorithm. A neural network is a set of connected input-output units where each connection has a weight associated with it. In fact, the motivation for this neural network, artificial neural network, is a human neural network. That means our brain is a neural network, right? It is a neural network. It is a interconnected network of billions of neurons. Okay. When we look at, let us say, to give an example, when a human being look at a particular scenery or a landscape, that means will give an excitement, right? If it is really awesome. Let us say if you go to if you go to an Ooty for the first time, by seeing those tea gardens and so on, you may get excited, right? You will show that on your face, even voice also, in the form of voice. That is the input. That means input is that Ooty tea gardens, and the output is your excitement, your expression. Oh, awesome, something like that. Okay, that's how our human brain processes that input by a neural network inside our brain, and it gives the output. Similarly, the same model is emulated as emulated as artificial neural network. That is the human brain is basically main motivation behind this evolution of these artificial neural networks. Yeah, during the learning phase, the neural network learns by adjusting the weights so as to enable to predict the correct class level of the input tuples. This is the learning phase. The learning phase, basically, the weights are updated. Okay, weights are updated in the neural network. Once the learning is stopped, yes, then all the weights are updated. Those are fixed now. Now the new test data item is given to the neural network. Then it will be able to classify the given data item or test data item. That's all. Yeah, maybe I'll just I'll give this somehow it looks like this: a multi-layer feed-forward neural network. You have input layer, hidden layer, and output layer. There are 3 layers. The input layers generally that means like the human. If you look at here, you'll see the scenery or a tea garden. Tea garden is represented as x1, x2, xi, and xn. In fact, and the hidden layer is only one hidden layer is known, but in reality, in fact, you have many hidden layers. This is our brain. Inside you have a lot of processing happens inside the hidden layer, and the output layer you will get the excitement like, oh awesome, your expressions will come in here in the output layer. So the processing happens. Yeah, these weights are represented like signals. You see, once you see the scenery, the signals are flown through right in your brain, and those signals, the strength, maybe signals, maybe electric pulses, those values are represented in the form of the weights here. Okay. So this is a quick idea of it. Likewise, for every edge here, the line is associated with some weight. Now, these training phase, we are going to initially will assign some values to these weights, maybe in the range of some -1 to 1. Okay. Later on, we'll update it as with the training data. You have label data. Label data is given to the input layer, and we keep on adjusting the weights based on some algorithm. That is a back propagation algorithm. Okay. Just quickly, we'll see. Yeah, these are, you can just look at it. Yeah, somebody may put a question like how many units should be there, right? That is, in fact, it's very challenging to determine. I think in the beginning, professor asking about it. It is not very easy kind of thing. Okay, network topology generally specify the number of units in the input layer. Generally, it goes to the number of attributes or features, number of dimensions. For every dimension, ideally, you need to have one input layer, then the one input neuron, right? The input neuron. Number of hidden layers depends on the complexity of the data we have. The more the hidden layers, maybe you may need to have the more complex relationships, non-linear relationship, non-linear relationships you would like to model. Maybe you need to have more hidden layers. Okay, yeah. Number of units in each hidden layer and number of units in the output layer. This is more of many cases. We can use some guidelines already given by some researchers in this area. But even then, we need to figure out which one is right for us for our application. That is, generally we'll normalize the values for each attribute or the dimension measured in the training table in the range of 0 to 1. Output generally output on the output layer. Generally, if you have one unit for two classes, one unit, two classes means that is binary, something like binary, yes or no kind of thing. Then one unit is enough in the output layer. If it is many classes are there, then for generally more than two classes, one for each class, one neuron is taken into consideration in the output layer. Like if there are three classes in the output layer, you will have three neurons. Okay, these are some general guidelines. Yeah, generally the initial weights are assigned some using some random generation method, or maybe you can fix all ones, or maybe some random number can be generated between -1 and 1. Those are the initial weights that forms the initial weight. Using back propagation algorithm, we'll try to update the weights. Let us see. Initialize the weights to some small random numbers associated with biases. Propagate the inputs forward. In the sense, inputs is given fed at the input layer. Then you will see the, of course, we will have the activation function. We'll see activity function subsequently. Once you see the output, there is the actual output and predicted output. Actual output is the one, there is a label, actual label of the training data, and predicted one. If you exactly match, fine, there is no error. Generally, it will not be the case. Generally, you will not get exact match initially. So then that difference, put it in informally, that difference is error. That error is propagated back and update the weights. Terminate condition, when error is very small or predefined number of iterations are completed, or epochs, we also see one iteration we call as one epoch. And we can also fix the number of epochs. Then we'll stop the training the neural network. So here you can see the activation function and so on. This is the input layer. First one x0x1 inputs, then weights, then in the activation function in each, this generally happens in the each neuron hidden layer, particularly in the hidden layer. Okay, a sigma, that is, you will sum it x0 into w0 plus x1 into w1, xn into w1. There is a combined input. That combined input is summed, and Bias is something like it is something like if this summed input is greater than some threshold value, okay, then only this neuron is triggered, or it exceeds the threshold, because sometimes more excitement, less excitement we have, right, depending on what we see. To decide that, we'll use this bias component. Okay, yeah. And activation function, this activation function, maybe this we'll use, generally we have sigmoid or ReLU functions and so on. There are many activation functions which will collapse this combined input to the range 0 to 1 or -1 to 1. Yeah, generally efficiency of this feed-forward network is something like, for each iteration, if you look at it, so number of tuples, that is number of training tuples, that is mod D multiplied by W, that is number of weights. Okay, so it is in the order of this. In the worst case, yeah, this is a backpropagation algorithm. Just I have given a quick idea earlier. Generally, initialize the weights and biases in the network. Then, while the termination condition is not satisfied, for each training tuple, what we'll do, we'll feed them or push them forward in the input layer and compute the output. You see the compute the combined input for each hidden layer or output layer. Ij is equal to what, sigma wij oi. This is what I explained to you already. Plus threshold you add it and apply the activation function. In this case, it is sigmoid function is applied. Okay, sigmoid function, and for each unit j in the output layer also we will find out the output. Then error is computed. This is the formula for computing the error. That now similarly errors are computed. Then for each weight in the network, this using this error we are updating the weights. That is delta wij. Then that delta wij is added to wij. Similarly, threshold is also, biases are also updated. So likewise, this is a quick algorithm, backpropagation algorithm to update the weights. Like for each input, for each training tuple, you do this process. Likewise, if there are 100 training tuples are there, 100 iterations, you will do this. Okay, yeah. So this is something like this. Initial weights x1, x2. This is x1, x2, x3. These are the weights. This is very simple network. And I have a training tuple here given x is equal to 101. The class has 1. Okay. Now this is the initial configuration is given here. Initial configuration is given randomly. Now you are going to find out net input for the unit j, the unit 4, the neuron 4, 5, 6. This is how you will find out the net input. This is output. This is after applying activation function, you will get this output. Errors. See, from the output layer you will start. From the last layer you will try to compute the error. Yeah, this is 1 is the actual label. If you look at this 1 minus 0.474, this is actually what we got. That is the output. If you look at here, output 6, see 0.474. If you look at here, net output 0.474, right? Actual class label is 1 there. So that's why I'm taking 1 minus 0.474. And similarly, yes, error is also computed. This is how error is computed. You can just see the formula. You will get to know. It's pretty straightforward. So errors is computed for every unit. Similarly, weights also updated now using this error component. This is new value. The new values are old values and new values are shown here. Once these are updated, now for one tuple we have done it. Now of having likewise repeat this training process for all the training tuples. Now you want to classify a new tuple. There is a test tuple. Let us say 110. How to classify? What is the procedure for classification of this? So this is pretty straightforward. You will not propagate the error here. Only you will just supply this 110 to, let us say 110 will x1 is 1, x2 is 1, and x3 is 0, and just push it here and find the combined input here. Apply the activation function. Okay, and that will become input to this 6. That is multiplied with W46. There is a weight already obtained. Similarly, for 5 also, you will get the output of this 5 and multiplied with this W56. That combined input, again apply the activation function, and you will get some output for the unit 6. That output, based on if the output is generally greater than 0.5, we call it as it is a positive class. If it is less than 0.5, we call it as a negative class. Okay, if it is a binary classifier. Okay, so this is how we are going to classify the given neural network. Okay, yeah. With this, I'll conclude my session. In this presentation, to summarize, we discussed about some of the advanced concepts in classification, particularly semi-supervised learning, where we use labeled and unlabeled data, unlike supervised and unsupervised learning, where we use only either labeled data or unlabeled data, but not both. Next one is multi-class classification. Whenever we have only binary classifiers and the task is the multi-class classification, then we need to use many approaches like one versus all versus all, or error code detection, and many more such methods. We can use it to classify a given test tuple to one of the classes. Active learning is also, we can treat as one of the variations of semi-supervised learning. Here we have few labeled data and many unlabeled data. As then, to create labeled data, we seek the opinion of some human expert and will retrain the model. Transfer learning. This transfer learning here, if you have already machine learning model for few of the existing tasks, the same knowledge or the learning gained through these models can be used for building the other models for the newer tasks. Okay. In fact, the pre-trained models in the deep learning are very common, and they use this transfer learning a lot, particularly in the CNNs. First few layers will be as it is, and maybe last layer will be trained for the new task. Then reinforced learning. This is something like to bring in creativity. Maybe the reinforced learning mostly the agent, the software program, software agent, or maybe example is some robo, will try to learn from the environment through its various actions by some predefined program, or may not be completely from predefined program, maybe by trial and error fashion as well. Okay. And we have concluded our talk with the artificial neural network. There's a basic quick introduction to artificial neural networks, which is for which the motivation is basically our human neural network. Okay. Thank you, friends. Happy to, I think, hope you gain some quick idea about various these advanced topics in classification. Yeah, thank you. If you have any queries, it is now open to the audience and the organizer. Sir, I am done.
Yes, sir. Thank you very much, sir. You gave a very informative session, and probably few participants may interact with you, sir.
Yes, sir. Now it is open.
Yes, sir. If there are no questions, can we wind up, sir?
Hello,
Yes, sir.
sir.
Yes,
One
sir.
question. Hello, one question. In reinforcement learning, what exactly are the algorithms that are currently there?
Sorry, ma'am. Can you repeat?
In reinforcement learning, what are the algorithms that are there currently?
Ma'am, there are many actually. Actually, there are many, but at this point of time, I didn't explore. Actually, I didn't explore. My talk is just only generic, very generic. There are many, ma'am. You can just find out recent one. There are many algorithms. Actually.
Okay, sir.
Yeah. Even in fact, using label data also, label some maybe pre-trained way also there, or trial and error way also there. Maybe model free or model based. They classify algorithms into model based and model free based learning algorithms. Okay. Yes. Yes. Thank you, professors. Thank you for giving an opportunity. Thank you so much. Have a great time. Happy learning.
Yeah, thank you, sir. So, sir, can you share your PPT, sir?
Sure, sir.
For
Sure,
the
sir. I'll send it to you through email, sir.
Okay, sir.
Okay. Sure,
Okay.
sir.
Thank you
Thank
very
you,
much,
sir.
sir.
Okay.
Thank you all participants. So we will join positively by 2 o'clock. Thank you all.